Hello everyone, today in this video we are going to talk about Gauss law. So after this video you should be able to derive Gauss law and apply Gauss law to calculate electric field or electric flux. So this is the statement of Gauss law and it says the total flux through a closed surface is 1 by epsilon naught times the charge enclosed by the surface. So suppose I have a charge Q inside a closed surface. That time the total flux through this surface will be given by this formula, that is 1 by epsilon naught times the charge. So epsilon naught is the permittivity of free space and Q is the charge enclosed. This is the Gauss law. So we can modify this Gauss law. We already know flux is closed integration of E dot ds, dot product of electric field and the area vector. So instead of phi I can write closed integration of E dot s is equal to Q naught by epsilon naught. So this is another form of Gauss law. So to apply the Gauss law we need a surface called Gaussian surface. So Gaussian surface is any imaginary surface which encloses a charge. So out here you can see this is charge plus Q and it is being enclosed by a closed surface. And some examples of closed surfaces are a sphere is a closed surface, a cone is also a closed surface. If you take a cylinder is also a closed surface. So a surface which is closed from all the sides is called closed surface. So now we will prove Gauss law or we will derive Gauss law. So in order to derive the Gauss law we take a charge and outside the charge we consider a Gaussian surface and the radius of this Gaussian surface is small r. So Gaussian surface is nothing but an imaginary closed surface. So this is charge and we are considering an imaginary spherical Gaussian surface. Q is the charge inside. So on the surface of this Gaussian surface I am taking a small area ds. The direction of area vector will be perpendicular to this small area, so ds is the area vector of this area and let E be the electric field at this point. And you can see the direction of both electric field and charge is in the same direction. That means both the vectors are going radially outward from the charge. So now electric field at this point at distance r from this charge Q will be given by this expression. E is the electric field at this point. Electric field at this point due to this charge will be given by E is equal to k q by r square. So this is the formula of electric field. Now we will find the flux through this surface. So flux through this small area ds will be given by d phi is equal to E dot ds, because this is the formula for flux. Flux is dot product of electric field and area vector. So now this can be written as E ds cos theta, and we already know the direction of ds and E is same out here, so theta is 0 degree. So I am putting theta is equal to 0 degree out here, so cos 0 is 1. So flux through this small area ds will be given by d phi is equal to E ds. So if we use equation number 1, that is if we put the value of E, then we will get this expression. So d phi is equal to k q by r square into ds. So this is the small flux through the small area ds. Now if you want to find the flux through whole sphere, then we have to add the flux through all the small area ds. So that means we have to integrate the flux through ds. So total flux is the integration of small flux through small area ds. So when you put the value of d phi, then you will get this. So I'm using this circle in the integration because we are integrating through the closed surface. Now out here k q by r square is constant, so I'll take them out. So I'm left with integration of ds. So now when we integrate this ds, so that means if we add all the small area on the surface of the sphere, then we'll get the surface area of the sphere. and surface area of the sphere is 4 pi r square. So out here you can see, if we consider all small area throughout the sphere, then we get the surface area of sphere. That is why I am writing integration of ds is surface area of the sphere. If you put ds is equal to 4 pi r square out here, then you will get this. Then r square can be cancelled out, and I'll put the value of k is 1 by 4 pi epsilon naught. So this 4 pi and this 4 pi will get cancelled, so you are left with phi is equal to q by epsilon naught. So this is Gauss law. So flux is equal to 1 by epsilon naught times the charge, and this expression is Gauss law. So we have derived the Gauss law. So now if you see the expression of flux through Gauss law, then it does not depend on the distance or shape and size of the sphere. So if you take a charge, suppose 4 lines of electric field are going. So if you draw one sphere out here, then 4 lines are crossing this sphere, and if you draw the larger sphere, only 4 lines will cross the sphere. That means flux do not depend on the distance, shape or size of the Gaussian surface. So out here both the spheres S1 and S2 are having same amount of flux, that is 4 electric field lines. So now you can try this question. A charge q is enclosed by a spherical surface of radius capital R. If the radius is reduced to half, how would the electric flux through the surface changes? So it is saying there is some flux through a larger sphere, and what will happen to the flux if we reduce the size of the sphere? Whether the flux will increase or decrease, you have to explain the answer. Now this is another question. A spherical Gaussian surface encloses a dipole. What is the flux through the surface? So inside the Gaussian surface we have a dipole. So according to Gauss law, we know flux is equal to charge by epsilon naught, and we know in dipole there are equal and opposite charges, plus q and minus q. So if you add plus q and minus q, you will get 0. So that means the flux through a surface which is enclosing a dipole is 0. So there will be no flux if there is dipole inside the Gaussian surface, because the total charge will be 0. There is a positive charge in the center of Gaussian surface of a radius this much. So we have to calculate the flux through it, and we already know from Gauss law flux is equal to q by epsilon naught. If you put the value of q out here, you will get the answer. So you have to find the remaining answer. So this is the next question. Calculate the electric flux through each of the 6 faces of a closed cube of length L if a charge is placed at the center of the cube. So there is a charge at the center of a cube. We have to find the flux through each face. So according to Gauss law, flux is q by epsilon naught. So q is the charge enclosed. So flux through 6 faces will be q by epsilon naught, but we need the flux through one face. So flux through one face will be 1/6 of this. I'm dividing this by 6. So this will be your flux through one face of the cube. So this is the end of the video. Please don't forget to like the video.